Okay, so we're recording now. Let's just do it together. Okay, so here this one's a little bit different, right? Mostly because we're assuming we have an investment, right? And it's $8,400. You know, we invested, I don't know what we invested to, but for now that doesn't really matter. We're going to write a formula for the function f of x. And that's going to give us the value of it x years later. And we're doing that for each of these situations below. So for the first one, we're assuming the value is increasing by $700 per year. Well, you tell me, tell me this, is that going to be an exponential function or a linear function? Anyone?
That's linear, right?
Yeah, linear, that's right. Because it's changing by a dollar amount. If it was changing by a percent, then it would be exponential. Right. So for the first one, that's linear. And so is the second one, right? Because it's changing by a dollar amount. And these three down here, 3, 4, and 5, since the value is changing by a percent, those are going to be exponential. In fact, here are the answers. You can see that for the first one, it's increasing by $700 per year. So this is basically our rate of change or our slope, right? 700 times x. And of course, the initial value is the 8,400. For the second one, I'm telling you that it's decreasing by $200, right? So that tells you it's linear, but also that the slope is negative 200 because it's decreasing. And again, it's 8,400. That's the initial condition, the initial value. Now for 3, 4, and 5, those are going to be exponential, as we can see. Well, actually, you can see it from here because the value is changing by a percent. In 3, it's increasing by 6.5% each year. So that tells you our R, it's going to be 1 plus R because it's increasing. And the R is 0.065. For the second one, it's decreasing. So it's 1 minus, right? 1 minus R, where R in this case is 0.081. It's every 2 years, though. So it's just like the previous example, we're going to have x divided by 2. Here, for number 5, it's every 6 months. So it's just like before, it's twice a year. And the R, of course, is 0.09. And it's increasing, so we have addition here. So I thought this was a kind of a fun example. You know, you don't want to forget about linear functions, okay? Right? They're changing by a fixed amount. Exponential changes by a fixed percentage. So that was fun. Now here's another fun example. I was going to have you guys try it. What time is it? I really want to get through. Well, I guess we could do this together. Yeah, let's do it together. So let's suppose we have $1 and we're investing it. But that investment somehow doubles each day in value. You know, this is actually an example I probably would use to introduce exponential functions, but I think it's fun to do it anyway. So we have $1, you know, we put it into an account or something, and somehow it's a special account where the amount doubles every day. First, we're going to write a formula for the function value, which is the value of the investment x days later. Okay? Well, again, since it's doubling in value, what that really means is it's going to be exponential. For instance, at time now, which is day 0, right? You know, we deposit, we still have just $1. A day goes by, The investment is now worth $2. Another day goes by, one day two, it's going to grow by $2 because it's doubling in value. So it's up to 4. And then another day goes by, it doubles in value. It goes up by 4. Notice right away it can't be linear, right? The amount of change is not the same. Here it's changing by 1. Here it's increasing by 2, increasing by 4. So it can't be linear. However, this is true. If you were to calculate the relative change every time you increase your input by 1, the relative change is always going to be 1, meaning our R is always 1. Basically, if it doubles in value, it's growing by 100% because you're adding on the full value. So again, this is you're taking f of 0, you're adding 100% of it to get f of 1. To get f of 2, you're taking f of 1, you're adding on 100%. So you're not adding on a fixed amount, you're adding on 100%. So R is 1 as a decimal. And so this is our function. I mean, the 1 is here, that's from the $1, but 1 times anything is the anything. No, excuse me, let me say it again. Multiplying by 1 doesn't change anything, so I left the 1 off, but this is the function we get, 2 to the x. Well, how much is the investment going to be worth in 10 days? Well, in 10 days, it's going to be 2 to the 10, which is $1,024. Now, here's the fun one. For number 3, would we take $1 million, or would we receive from the investment how much it's worth 20 days later? In other words, I'm basically asking you here, in a sort of comical way, is f of 20 worth more than $1 million? Well, it turns out the answer is yes. In fact, f of 20, you get this. I think actually if you do f of 30, so if you wait 30 days later, you get more than $1 billion. So exponential functions, they're different. And really what I'm trying to illustrate here is they grow pretty fast. They grow in value very quickly, much more quickly than a linear function does. Okay, I thought that was a fun one to do. Now, let's do some backup examples. So here's the first one. We had a shirt, and it was marked at $24.95. But at the register, I guess it's on sale, and they forgot to tell us. At the register, it's $19.96. What's the percent discount of the shirt? In other words, what they're asking is this. I know these aren't in the post notes, but in the notes I sent you, but I will post them. When I post the notes, this will be included. But this is basically asking you, what is the percent change in the price of the shirt? Well, what do we get? We have to calculate the percent change, right? And that's this. Essentially, you're getting the relative change and converting that to a percent, right? The new value minus, the ending quantity minus the starting quantity divided by the starting quantity. This was the price it started at, and we took off a certain amount, $4.99. So it decreased by 20%. So the shirt lost 20% of its value, if that makes sense. The negative is okay. That just tells you it decreased in value. Okay, that was fun. Let me just pause this and get the recording going again.